Hello, everyone. Welcome. Thank you so much for coming. And thank you so much to the organizers for putting on this incredible conference. I hope everyone has enjoyed themselves. Today, our talk is called C.A.L.L.I.N.G. Now I'm calling you now. And if you're not lucky enough to be a 90s pop fan, that is a lyric from a song from Aqua's debut album, Aquarium, where the song is about a lover who's trying to connect with their love, and they're trying to call, and they're just getting a busy signal. So they're calling to an operator and saying, hey, can you please connect me? Today, we're gonna tell a story about some pods running in Kubernetes that were crushing a little too hard on the Kubernetes API. I'm Terra Tauri. I'm a staff software engineer at Grafana Labs, and I'm joined today by my co-presenter,
Mario Macías, also staff software engineer at Grafana Labs.
So today, you're going to learn a little bit about eBPF. We're just going to go into the basics of eBPF. If you want to know more and the nitty-gritty details, Mario has a talk just after this in this auditorium that you should definitely come and check out. We're going to talk about how in enriching Kubernetes or enriching eBPF data, we broke the Kubernetes API. Why we needed to enrich that data and what we do to do that in Bela, and then how we ended up scaling that enrichment process. So, before I go on, can I get a show of hands? Who here is familiar with eBPF? Okay, so about half the people. Who has written an eBPF program? Okay, fewer hands. And who has deployed that eBPF program into production in Kubernetes? Okay, awesome, thank you. So before I go on, I need to set the stage and start and tell you a little bit about eBPF. So eBPF, if you don't know, it enables safe and efficient extension of the Linux kernel. Now you might say, we already have kernel modules. Why do we need eBPF? Well, if you've ever run a kernel module, you know that if the kernel module crashes the whole system. Everything goes down. What eBPF does is it introduces a virtual machine, the eBPF virtual machine, and that enforces halting as well as a few other safety properties that enables you to run these kernel extensions in a safe way. Now, I think a lot of people, when they think of eBPF, they think it's sort of a newfangled technology. But actually, the stuff that we're talking about was added to the Linux kernel in 2015 by Daniel Borkman. We're talking about the TC egress ingress hooks. And that is what allows us to snoop on network traffic. Lets us get our grubby little paws on all those network calls so that we can construct these amazing service graphs that we use in other products. But kernel data by itself, especially in Kubernetes, is really not that useful. If anyone who's SSH'd into a container knows that if all it has is cat and sh, it's really annoying to go into /proc and look at every single detail about every container. And especially when you're doing this at scale across an entire fleet of machines, it gets very tedious. So as I said, kernel data is raw, right? And in Kubernetes, every single node in a standard deployment has its own kernel. And that kernel data is giving you information about the source port, source IP, destination port, destination IP. But that's not what we care about in Kubernetes, right? In Kubernetes, we care about Kubernetes objects like services and pods, nodes. So how can we take this raw data and turn it into something that is actually useful for humans that care about Kubernetes? Well, as I mentioned, every node has a kernel. Kubernetes has a construct called a daemon set that allows you to run one pod per node. So that effectively gives you one pod per kernel. So that's how we solved kind of the first problem of running eBPF in Kubernetes is we have now one pod running on every kernel, and so we can gather that information. Still, we need to get this metadata because pod IPs are constantly changing. we need to know about pods and services so that we can provide useful information to people. Kubernetes has this incredible API, which is arguably what makes Kubernetes so powerful, right? You can set the state in that API, and Kubernetes will just go and reconcile your system such that what you've represented in the API becomes reality. And so we thought, well, there's this very tempting API that knows everything about everything that's happening in the cluster. Why don't we just ask that? And so why don't we just have every single daemon, or every single pod in the daemon set, ask the Kubernetes API? What could go wrong, right?
Thank you, Terra. Bela is built using a pipeline architecture in which data is extracted in early stages, is joined, is transformed in other stages. In one of those stages, we want to decorate metrics with Kubernetes metadata to make those metrics more meaningful for the final user. We might have, for example, for network level metrics, a source and destination IPs of all the pods that you are connected. From the eBPF side, we have access to the system level metrics at the network packages or row connections. And from eBPF, we can see source and destination IPs. But for the final user, those metrics are not usually so meaningful because we don't really memorize or we don't have a mental map of which IPs belong to which node. So we want to decorate those metrics in a given stage with Kubernetes metadata. This is pod name, namespaces, other levels, and so on. So in one of those stages of the Bela pipeline, we get metrics decorated with source and destination IPs, and we send out metrics decorated with Kubernetes metadata. This Kubernetes metadata is acquired using a Go library. Bela is mostly written in Go. There is a Go library named Kubernetes Informers. This library connects to the Kube API, and on one side, it retrieves a whole snapshot of your cluster. I mean, all the pods of your cluster, nodes, services, names, metadata, IP addresses, and so on. And also, it watches for any update into your Kubernetes cluster. This is a new pod is created, a pod has changed the IP address or has new IP addresses, a pod is destroyed. So giving as input this constant flow of Kubernetes object, Bela maintains an in-memory map that for each IP address, also it can also use other keys like container ID, PID, and so on for other kind of metrics. But basically, we maintain an accessible map for a given IP, which Kubernetes object it belongs to. So in that pipeline stage, we can provide extra information that might be meaningful for the final user. Bela runs one, as Terra said, one instance on each node, and that worked pretty good at first until we deployed in production in a large cluster. We already had Bela deployed in production. Nobody complained. Everything was OK. But one day they thought, hey, so we deployed, and happily we say, OK, let's go home. But someone else say, this cluster is not working. Whatever is happening is not working. And that is because we passed from the Kubernetes API server, went from few tenths of requests per second to more than 2 million requests per second. Also, the error rates of those API requests went from 0 to 10,000. And yeah, we also even lost some metrics because that started working. That caused that not only the decoration of metadata stopped working in Bela, but also some other Kubernetes objects were not properly reconciled. So basically, we took down the cluster with Bela. Some users also report it, but I have to be honest, we ignore them. Say, okay, maybe you are doing something weird. They even provide some public, they shared in our GitHub request some memory information, actually, enabling Bela in their cluster doubled the memory consumption of the Kube API. So we said, okay, our early users are complaining, we cannot deploy it internally, so we need to do something. What was happening behind the scenes? Bela runs as a daemon set. We have one Bela on each node. And to get metadata from the Kubernetes objects, it contacts to the kubelet that exposes a local endpoint in which we can ask for, in that case, pods, nodes, and services, which is anything that can have an IP, we want it. But the kubelet only maintains local information about the pods, especially. But since we are tracking network metrics, we also want to know the source IP, which is local, but the destination IP, we also want to know for external pods. So we need, each Bela instance needs to maintain a snapshot of the whole cluster. So when Bela, this Informers API, contacts the local kubelet, each local kubelet, this is a simplification, so it's, probably, it might be more complex, but just to understand, each kubelet sends a request to the Kube API, and for each request, the Kube API sends back a request for the other kubelets. So if we have 3 nodes, when this kubelet sends a subscribe, Kube API will send it to the other pods. So each node will receive 2 more, in that case, only 3 nodes, two more requests just to send the pod information, to share the local pod information with the other nodes. For few nodes, that's okay, but this Kube API is handling a number of subscriptions with an order of complexity of power of 2. It's fine for few nodes, but given when you reach a critical number, then memory, CPU is too high, you take down the cluster. So we were discussing how can we fix this, because not decorating our metrics with Kubernetes metadata was not an option, because the instrumentation will become mostly useless in that case. So first we thought about replacing the subscription model just by individual requests, because even at the end, if we store a snapshot of all the pods, we don't really need, or we mostly, Bela won't mostly manage information from all the pods. So what if we just ask, it wouldn't work well because the API is not well designed to efficiently query by IP, but just by name. And also even during the deployments, at the initialization of each instance, the Kube API will get anyway a stampede of requests. We were thinking about, okay, why we don't get the information from the local information from the Kubernetes API, which is somewhat undocumented, is not so much designed for the final user, but for internal behavior. But we don't get global objects to it. I mean, we can only get local pods. So we were thinking on clustering, creating a cluster cache, but that we will ending up getting similar problem. With a gossip protocol to share metadata, we will add some network traffic and complexity. So we decide to move to a centralized cache deployment. So instead of integrating this informer's code on each Bela instance, which run as a daemon set, we will create an external pod that it's deployed. It deploys few replicas. It can be one replica, two replicas. I don't know. It depends on the size of your cluster. And this cache pod will implement the Go informer's code to subscribe to the Kubernetes API from few instances and get a complete snapshot of all the pod metadata, which is later shared with each Bela instance that connects to this cache service. At the end, what we have is a two-level cache. Even if we say centralized cache, it can be distributed because you can have multiple instances, and then each Bela will connect to different instances using some load balancing. So this cache instance pod connects to the Kube API, gets all the informer metadata. If you request for a pod metadata, for example, you will see a big YAML file or a big JSON file with a lot of metadata that actually we don't really need all that metadata. So that cache instance just stores the minimal needed snapshot of the required Kubernetes object. That is name, namespace, kind, the owner, and some labels and annotations, which is the metadata we really care for decorating metrics. And Bela is connected to that cache instance using a minimal protobuf definition via a gRPC stream. So the network and the resources required for transferring all this information from the cache to Bela is much lower. And at the end, Bela also, once receives the information, it keeps updated an internal database, mapping IPs, container IDs, qualified names to the metadata objects. Decentralized cache is storage-less. We wanted to make it as easy to maintain as possible. So we didn't want it to require a storage system. We didn't want it to require some extra communication, like a message queue. It's just plain gRPC. That means that if by some reason this pod crashes, maybe a bug, or maybe it gets too many resources and gets OOM killed, when a pod restarts, the cache pod restarts, another pod will be started, will reload the snapshot, and Bela will connect to that new pod. In that time, Bela will still maintain its local copy of the metadata. So Bela will miss some updates, but most of the metrics it gets and needs to decorate, Bela will find the metadata for most of those metrics, given that this cache pod instance takes few seconds to restart.
So some issues that we ran into with this approach, centralized cache solved the primary problem, but as we know in tech, everything is a trade-off. The main reason why we really evaluated a number of options was we didn't want to introduce another component for our users to manage. Everything that you run in Kubernetes adds toil. You got to upgrade it. You got to check the resource utilization. And in this, also, the resource utilization, especially during startup, because the cache is empty when the pods first start, it has to refresh its brain about everything that's happening inside the cluster, because the caches maintain a state of everything that's going on. And so during startup, there's this kind of thundering like storm of requests that it makes to the Kubernetes API to get information about everything, a whole bunch of deserialization that needs to happen there, and then also serialization that happens when the daemon set requests information from the cache. And so you can see here, for the first minute or so, when the cache is starting, resource utilization is almost double the steady state. So that's a very important thing. Make sure you're leaving headroom when you're deploying this cache. That's something you got to think about there. And so when you're setting your requests and limits, obviously, in the pod. We can see here the Kubernetes app showing that, yeah, the resource utilization is twice what it would be normally. This here, we have some Pyroscope profiles showing, this is how we kind of dove into what was causing the space and time complexity, and we found that it was mostly from deserialization, and that's what was causing a lot of memory utilization on startup. So we solved that by just storing, as Mario mentioned, just storing the specific information that is necessary, not the whole Kubernetes object, but just the stuff that you've configured that you want to have decorated. And another thing that we did too was on the client side, we changed that to be a gRPC subscription, so that way it's binary, and the binary encodings reduce the memory utilization of serialization to those requests. So I think in summary here, the Kubernetes API can handle a lot, but like everything in life, it has limits. And our solution was to introduce a centralized cache, as we've kind of described. And I think like a general takeaway that you could look at here is anytime you're deploying a daemon set into Kubernetes, you really need to think about performance. And when you're doing that capacity planning, it's not just the time and space complexity of the algorithms in that specific deployment, but you also need to think about the downstream impact on the various components, like the Kubernetes API, and think about, how is this going to affect us? That's the talk. Thank you so much. Does anyone have any questions?
Okay. Thank you for all your work. Huge fan. Baylor took one of our OpenShift clusters down too. When did you introduce this change? We started using with Baylor 2.0, I think.
I think this change was released in Baylor 2.9, 1.9 or 2.0, but you need to enable it on purpose. So by default, Baylor will still run in the old mode, but if you are, for example, using the Helm chart, there is an option that is Baylor cache your instances or so on, that if that number provided is different than 0, it will automatically deploy that cache instance and configure Baylor to connect to it.
Thank you.
In the meanwhile, if there is another question, this cache is an independent component. We designed it for Baylor, but I think it covers some use cases from other teams that I've met here, other people having the same problem with informers and API starvation. So it's an open service with an open protocol with libraries, so it can be also useful in addition to Baylor, even if you are not using it for Baylor for you. Okay, so thank you for your attention.
Thank you so much.